Hello, this is ET250, lecture 19, and today we're just going to do a short review over the midterm 2 list of concepts, and then just two simple example problems, one on trig and a little bit on the Bode plot gain stuff, and then a mutual inductance. We've done a ton of examples on RC and RL, and if you go back to those previous lectures, you can see a pretty big monster problem. Okay, so what are some things that could be on midterm two? Well, of course, midterm one material, right? KVL, KCL, Ohm's law, all that good stuff that is on there. So make sure these fundamentals are strong. Strain gauge, Wheatstone bridge. The only thing really here is this was just for an example, but here it was like voltage divider. Okay, you built this in circuit in lab, but there shouldn't be too much here that would catch you other than voltage divider, I suppose. Now here, capacitors, yes, very important. I equals plus or minus C dV dt, same passive sign convention as Ohm's law and power. We have our fluid analogy. A capacitor is like a flexible membrane, all right? The construction is just two parallel plates. So a plate like this and a plate like that. Don't confuse this symbol, by the way, with a voltage source. Sometimes a voltage source is drawn with two parallel plates, but it's really like a voltage cell, and one plate is longer than the other. The longer one denotes the positive terminal, but here, two parallel plates is a capacitor. The energy in a capacitor is 1/2 CV squared, okay? And then you got to remember how to combine them in parallel and series. For capacitors, opposite of a resistor and an inductor. In parallel, they add, and in series, they add by the reciprocal. So don't get that messed up. Okay, in inductors, it has nearly the same equation. Of course, you got to change the C for an L, but it's V equals plus or minus L di dt, right? Notice the duality here. Here's V, here's I for the derivative, here's the non-derivative I and V. So V equals plus or minus L di dt. Notice the plus or minus, again, passive sign convention. We see that a lot, okay? The fluid analogy, it's an inertia water wheel, right? It takes some time to get spun up, right? The construction is very simple, just like the capacitor. So simple, it's like a coil of wire, not too bad. And they're usually wrapped around a highly permeable piece of material like iron. Okay, the energy stored in a capacitor is 1/2 Li squared. Okay, notice again the duality here. Instead of V, it's an I, and instead of C, an L. Parallel series, just like a resistor. So you add them up in series, and then you add the reciprocal in parallel. Okay, integration derivatives. Of course, when you have these forms, if you just have to have an understanding of what a derivative is, what an integral is, right? Integration is you think kind of adding up, right? Like if you had the speedometer of a car, and then you want to know the position, right? After a certain amount of time, you'd add up all those times the velocity, and you get to position. So that'd be integration here. Derivatives is what's slope, right? So just having that understanding, and if you look back to those previous lectures, we've done some examples on integration and derivatives for capacitors and inductors. Now, transient circuits, yes, that's a bit tricky if you haven't done these problems, but after doing a lot of these, I think these actually aren't so bad. First, you got to identify the boundary conditions, and of course, you can go to the previous lecture to see all the steps on how to solve these guys. You have the switching time. Now, this 0 here is indicating the switching time. It doesn't have to be at 0, it could be at like 3 or 10 or whatever it is, -5. The plus and minus is just right after the switch occurs, right before the switch occurs. And this is after the switch has been held down or held up for a long time, back to steady state. Now, for your capacitor inductor, you have different transition conditions across a switch transition, right? So across a switch transition, the voltage in a capacitor must remain constant, where the current in an inductor must remain constant, okay? Now, again, I repeat, this 0 doesn't have to be at 0. The switch could occur at any time, right? But the minus and plus is just right before the transition, and the plus is just right after the transition. Okay, steady state behavior. In steady state, a capacitor behaves like an open circuit and the inductor behaves like a short circuit, right? And you can go back to your physics here, right? So once that flexible membrane is, there's no more change. If there's no more change in voltage, it doesn't allow any current, right? And it just holds itself. For the inductor, you go back again to the physics, and it's like an inertial water wheel. Once there's no more di dt, there's no more voltage, and a short doesn't have any voltage, and a open does not have any current. Okay. You had this first order differential equation form, K1 e to the st plus K2, right? By playing with these numbers, you change the decay rate, the starting condition, and the ending condition, right? We had this concept of the time constant. The time constant was the time such that you got a -1 in that exponent. It describes basically how fast your system, your first order system decays or rises to get within 62% of its final value, okay? All right. What else did we talk about before midterm 2? We talked about trig, so the units of angle. So radians was something we kind of reviewed, right? Radians are good. We had the constant pi and tau. Pi is what, 3.14, tau is 6.28. I introduced tau. I mean, I didn't invent this idea, but the idea of using tau as 6.28 is, I think, a lot better. Now, we're always going to be stuck with pi, but I felt like this was much more intuitive, right? So you have 2 revolutions, that's 2 tau radians, right? Whereas you have to go 2 revolutions, that's 4 pi radians, right? So just that little factor of 2, why, right? A little bit unintuitive, right? Okay, cosines with time, V of t equals VP cosine of omega t plus theta. You got to know what these factors do. VP stretches that cosine out in the vertical direction. Omega stretches and squeezes that, that cosine in the horizontal direction. And theta slides and shifts that cosine on the horizontal direction. This theta here is sometimes quoted in degrees, so you got to make sure you get if you're calculating time, we'll see an example later, that you don't mess that up. You got to be consistent in your units, right? Either all radians or all degrees, and set your calculator to the correct method. This theta here, if it's bigger, it means it's what? It's more leading and it's shifting to the left in time. Okay, if this theta gets smaller and more negative, shifting to the right in time. So understanding what a different numbers here do to the plot will also be important. Okay, omega, period, and f, these are all interrelated. If you know one, you get all 3 for free. Okay, this is frequency is what? Cycles per second, period is seconds per cycle, and omega is radians per second. Okay, so these two are kind of the same thing, it's just in different units, cycles versus radians. You have to know peak time. Peak time is the time that the cosine peak occurs, and it is related to theta and one of these, okay? And root mean square. You can take a root mean square of any signal, but if you take a root mean square of a sinusoidal signal, it happens to be just the peak or amplitude divided by root 2. That's kind of the nice thing. We proved that in a previous lecture. Okay, and really it's the square average root, right? You take the square, then you take the average, and then you take the square root. Okay, filters. Filters are if you have 2 inputs, 2 signals, the filter's in the middle, and so the filter is the ratio of the output of the input, right? And we talked about high pass and low pass filter. For a low pass filter, if your input is slowly moving, then your output will match the amplitude. For a high pass filter, if the input is slowly moving, the output will be nothing, right? And vice versa. For a low pass filter, if the input is moving very fast, the output is nothing. And for a low pass filter, or for a high pass filter, if the input is moving very fast, the output will match and will also have nearly the same amplitude. We also talked about phase shift, which is the output phase minus the input phase. Okay, for a low pass filter, you see phase lag up to 90 degrees of the output. And then for a high pass filter, you see a phase lead of the output relative to the input. We looked at also a log base 10 scale. The benefit is that you get a large range and the resolution, so that's nice. And just some terminology, a decade is a factor of 10. Okay, and we looked at the dB scale. dB scale is also logarithmic. And then where's this 20 come from? 20 is actually 2 times 10. The 2 is actually a g squared, which relates power. That's the whole Bell scale. But then the 10 is the deci in decibel. Okay, so a Bell system is log base 10 of g squared, which is power. And the decibel system is the 10 times log base 10 of g squared. Okay. We look at Bode plots, which combined the dB scale on the y-axis and the log base 10 scale on the x-axis. This would be frequency, and this would be gain. We also looked at a phase plot where the y-axis was theta out minus theta I, and the x-axis was log base 10 of omega. So both of these had the same x-axis. Okay, good. And then the last thing we covered was transformers. So transformers, we had two equations, mutual inductance, so the general equations for a transformer. It's basically two inductors put side by side sharing the same core. So you're getting energy transfer, magnetic energy transfer between the two coils. And if this is an ideal relationship, the coupling factor of equals 1, you can get the ideal transformer relationships, right? Do these work well in DC steady state? No, they do not work very well in steady state. In fact, you don't even want to run them. Real transformers, you don't want to run them in steady state. You can blow them up. Okay. Dot convention and sign rules. The dot convention sign rules apply to both the ideal transformer and mutual inductance equations. We talked about how M is dependent on the number of turns and L and coupling factor, right? All the different forms, and also the construction, right? Pretty straightforward construction. That's why they're so popular. They're so powerful because you can make them relatively cheaply. I mean, their transformers, of course, are expensive, but you're making them out of simple materials, copper, steel, right? Yeah, so good stuff. Okay, this is all the concepts that we've covered since the beginning, right? Of course, you know, I haven't highlight all the midterm 1 concepts, but yeah, this is enjoy, bask in it, right? Okay, so let's do a simple trig example and a transformer example. And like I said, we've done so many of these. You can just go back to that previous lecture. There's a whole lecture dedicated to one of these examples. Rewatch that one. I think that is a monster problem that really picks apart the harder parts, right? If you can do that problem without notes, you're in good shape, okay? If you want to look at examples for capacitors, inductors, go grab those lectures and watch those. Okay, but let's just do a little one of these and one of these. Okay. Okay, so let's say we're given an AC signal using cosine. They tell us that the RMS voltage is 20 volts. They tell us that the period is 100 microseconds, and they tell us that the peak time is 20 microseconds. And they want us to find V of t, draw and label the points, and they want us to find these values, V at 20, 40, 60, and 80 microseconds. Okay. So if we want to find V of t, well, we got to fill in all these unknowns, right? The VP, the omega, and the theta. Okay. So before we even do the math, isn't it, I like to get a physical intuition of what's going on first, right? Even before we get the equation, let's draw it. Let's draw what we think this is going to be. So if I draw it here, here's time in seconds. Okay, so they're saying that the peak time occurs at 20 microseconds, which is here. All right, and so let's say we have and then they say that the period is 100. Okay, so this is 20, and then you get 100. So it's like this distance is like 5 times this distance. 1, 2, 3, 4, 5. Right. So that's let's see, and that's here. You're going to get a cosine that looks like that, right? So we know that this is your period. And then this is your peak time, right? Okay, that's not too bad. And we notice that we have a positive, we better get a negative phase, right? Because we're kind of lagging here, right? You guys see that? See how this peak time is lagging relative to the 0 time? Okay, good. And we are going to be asked for these voltages at these times, at 20. Oh, well, at 20, we better get whatever the amplitude is, right? That's the amplitude. What is this time? So if this is 100 and this is 20, what is that time? So half of this is 50, right? This is 50, and then this is 50. So this must be 70, right? Something like that. Okay. And then what is this 25? So this must be 45, right? Okay, so these are all in microseconds. All right, so we kind of have an image before we even crunch into the math of what's going on, what this is describing. Okay, so let's kind of keep going. So what's V peak? Well, we know that this times root 2 is the V peak. Good, right? Because V peak divided by root 2 is VRMS. Good, for an AC sinusoidal. So that means this is just 28.28. That makes sense. It's bigger than this. So this is 28.28. Good. And notice I put volts peak to make sure that my units indicate, am I talking about peak or RMS voltage, right? And here I put RMS so that once I see that number, I already know it's an RMS value. Okay, what about the angular frequency? Well, the angular frequency, like we said, if we know one, you get the other for free. And so we can just use our equations here. We know that the frequency is the inverse of the period, and then the frequency and the angular frequency is related by 2 pi or 1 tau f, right? And 1 tau is 6.28, 2 pi is 6.28, same thing. Okay, so then this f is just 1 over 100 microseconds. So that's, what do we have? 10,000. Okay, 10,000. And then if I want to get this, I just multiply this by 6.28. So omega is 6.28 times this, so 62,000. 62,831.9 to be exact. And so that's in radians per second. Okay, we're almost there. Now they gave us the peak time and we want to find theta. And so, oh, by the way, I have it written. Here's just other forms. So you could write it like this. It's 1,000 tau radians per second. So when you write it like this, you actually get to see the frequency embedded already, right? Okay, or 20,000 pi radians per second. And when I see this, I'm just like, my mind starts glazing over, like, I don't know. This is actually, I feel like, a useful way of writing it. I see, or immediately it's 1,000 cycles per second, right? And then I just need to multiply it by 6.28 to get the units and radians. This one, okay, but it is what it is. All right, so the peak time, we know the peak time equation is minus theta over omega. If you remember, how do we get that equation? It's just setting this to 0, right? Setting this to 0, you get that, right? And that, why do you set it to 0? Because that's when cosine is a peak. Good. And it looks like if we want to solve for theta, we know omega, we know peak time because it was given in this case, and we just bring that over and we get this. So we take 20 microseconds, which is here, and then multiplied by omega, no problem. And we get negative 1.26 radians. Well, how much is one radian again? 1 radian is when the arc length and the radius are equal. So look at the arc length here. This is the arc length, and the radius is about 60 degrees, so a little bit more than 60 degrees, right? Okay, good. So that's what this is the interpretation, physical intuition of what 1.26 radians is. Notice it's a negative number, so this thing's going to be lagging, right? Good, we get confirmation. Okay, and then if I wanted to convert it to degrees, I could, right? And yep, 72 degrees. Does that make sense? So this is 60, a little bit more, 70, 72, good. And then we just punch it in. So this would be your form. Now, here's something that's important to note. When you write down these forms, or if you're given these equations, typically they'll give you the units mixed. I kind of get why they do that, just because we're raised with degrees, and so it's useful to see things in degrees than radians. And so what we'll do is we'll put the degree unit here, but then we'll say that this is the radian per second. And yeah, that's kind of confusing, but intuitive at the same time, I suppose, right? I think it would be better if we just raised all of us on just radians. Just forget degrees altogether. Just everything is in radians, right? And then when we see these numbers, we put it all in radians, okay? Because that way, if we wanted to compute, for example, these voltages with time, so we want to put in time here, can you imagine? It'd be so tempting to just take 62,831.9, multiply it by 20, and then just literally add negative 72. And blindly do that, right? Think of how many math students have made that mistake of not remembering to get this in the same degrees, okay? Then the other thing you have to remember is my calculator set to radians or degrees? So when it does that calculation, right? Again, 2 sources of error, right? If we just stuck with one standard system, I think we would have, it would have been a lot better. So anyways, when computing V of t, we must unmixed, right? We must unmix. And so one way to do it is just bring this back to radians, so 1.26 here. And then we can now do things like plug in 20. By the way, we know that 20 microseconds is the peak time, so we better get a 1 for this cosine. This all better cancel out to 0 on the inside. And sure enough, I plug in my calculator, I get 28.28. And I can even pull my calculator out and try it. So if I take 28.28, can you guys see this? Let me see if I can turn on the light. There we go. 28.28 times cosine. And we said omega is this guy, 62831.9. Good. Times 20 microseconds, which is right there, 20 e to the minus 6, and then minus, now I got to use the radian guy, 1.26, 1.26, good. And what do I get? 28.28, good. Yep, so that everything's happy. Now, all I had to do here is go back to my calculator to calculate the different ones, 40, 60, and 80. So I just go in here and just change that 2 to a 4. So instead, right there, 40. And what do I get? 8.82. Okay, I can go back in here and then change it to a 60 here. What do I get? Negative 22.8, right? You guys see that? 60 at 60 microseconds, negative 22. And then I can do one more time to get the 80. I don't have to retype the formula. Love you, TI-89, 80. Again, I get negative 22.9. Okay, so those are the values I get here. Okay. All right, so let's go back and let's plot this. So notice my plot has the same thing. Good. So I have 20 microseconds, and do these points make sense? I have everything labeled now. At 40 microseconds, which is just before the 45, yeah, I have 8.81. That seems to make sense. At here, this peak, I have 28.28. Good. Over here, I haven't quite bottomed out, because if I bottomed out, I'm going to get negative 28.28. I get negative 22.87. And then here at 80 and 60, notice they're kind of they're at the same horizontal, and I'm getting again the same number, negative 22.87, right? So you can see that the values we're calculating are matching our physical intuition, right? Always you want to make sure whenever you calculate a number, does it make sense? Don't just like calculate a number, say, yep, that's good, and move on. You want to be making sure that makes sense. Okay, let's have a follow-up question. Follow-up question is, let's assume that this previous signal was an input voltage. And that a V out is an output voltage with the same frequency. And we're talking about like a filter here. And where V naught out or V out is 7.2 cosine of omega t minus 22. So this omega is that same 62,000 thing, okay? All right, so what do we notice about these two signals? Oh, it has a smaller amplitude, 28 versus 7.2. And it's minus 22 degrees in terms of phase, whereas the other one was minus 72 degrees in phase. So this is actually leading, right? Okay, what is the gain in dB and what is the phase difference? All right, so the gain in dB, well, G is equal to V out over V in, and then I just got to do that Bodhi thing, that dB 20 log 10, right? And so that's this guy, right? So G and dB equals 20 log base 10 of G, which is just output over input. Oh, I just plug it into the formula, 7.2 over 28.28, log base 10 of that times 20. If I plug that in my calculator, I get negative 11.88 dB. And so does that make sense? I get a negative value? Yeah, because the output is less than the input. On a logarithmic scale, if you get negative, that means that the gain is actually less than 1, right? And we can even do that. Let's just plug it into the calculator. So what do we have here? We have 7.2. Actually, we got to do log. How do we do log? So I think I have to go to my catalog log. Okay. Log of 7.2 divided by 28.8. And then times 20. And I get, well, no, not 28.8. I think it's 28.28. Is that right? 28.28. Yeah, negative 11.88. There it is. You see that log of 7.2. Yep, we're good, good, good. All right, so that's good. And I think that means that this number is actually 28.28, sorry. Okay, so what about the phase difference? Theta naught minus theta I. So output minus input in phase. Well, we already have these numbers. That's actually a pretty easy calculation. Minus 22 minus negative 72, that's positive 50. Okay, or if I convert it to radians, it's 0.873, right? 0.8 radians is the same as 50. Yeah, that makes sense. So what does that say? It's positive, so the theta out is leading. And we can already see that. This is a smaller negative number than this one, which was negative 72. Okay, not too bad. Let's just do one more simple example. Okay, so we have a transformer example, and they give us the L1 and the L2 and the M. Okay, great. And they have two current sources, and they say, let's say this current source is not a constant current, it's this 2 cosine 500 t. So this is an AC signal. And let's say this current here is a decaying signal, right? It starts at 2 and then goes down. So it's a transient signal, which is something we've seen already, right? Okay, so they're asking, well, what are the equations V1 and V2 look like, right? Well, we can just follow the mutual inductance equations, right? So V1 and V2 are this. So let's just make sure that these signs are correct. V1, does the I1 go in the positive terminal? Positive. Okay, what about I2? I2, the dot goes in, it goes into the dot, and V1 positive touches? Positive. What about V2? For V2, the self-inductance, this is going into the negative terminal, so that's a negative. And I1 is going into its dot, but V2 negative is touching its dot. That's two negatives, negative and negative. Okay, not too bad. And then what I can do is take the derivatives of these and just punch them in. Pretty straightforward example. So what's the derivative of this? Well, the derivative of cosine is negative sine, and I got to then pull out the 500, right? So I pull out negative 500 times 2 sine of 500t. That's easy. What about the derivative of this? This is also easy. So you just bring the negative 400 down. So negative 400 times 2 e to the minus 400t. And then I just pop these guys in, right? So very simple example, not too bad. And once I punch everything in, I see that I get this. V1 is this, and V2 is this, right? So this is this part here, L1, right, 0.04 times the di1 dt, which is this one, plus m, which is this, times the di2 dt, which is that, okay? And then what about this one? This is the same thing. That's minus L2, which is 0.03 or 30 millihenries times the di2 dt, which is that guy, good. And plus m or minus m times this, times the di1 dt, good. Now, let's just take one step further and see what these are doing. Well, as time goes on, what it's saying is V1 is going to be oscillating with a sign. And as time goes on, this term actually goes to 0. Right? And that should make sense. What about here? Same thing. This term eventually will just go to 0 and you're just left with this oscillation. Okay. Not too bad. Not too bad. Very simple example. Okay, well, please watch the other lectures in your midterm 2 review. And I hope these all work out for you. And I look forward to seeing great grades on the midterm 2 exam. Have a great day.